Hello, everyone. Welcome back to the MIT Climate Implications of Computing and Communications workshop. We are in the sixth and last session where we will have a panel discussion to share ideas and ongoing work on novel architectures and novel hardware for reducing the energy consumption associated with computing. And you have already heard a lot on the energy and sustainability implications of computing in this workshop, but I will start by reminding one key number. That is, the goal in the field is to improve the energy efficiency associated with computing by more than 1,000,000-fold. So that's the target that was recommended by the workshop and report that was provided to the field by the Semiconductor Research Consortium in the last year. So more than 1,000,000-fold. Where is this number coming from? It's coming from the fact that the field, us all, are working on improving the capabilities of computing, in particular in contexts of AI, where we want to come up with computers that can sense, perceive, reason similar to the human brain, and do this in an energy efficient way. And if we look at the compute energy trajectory from the last decade and into the next few decades, if we continue with the existing trajectory of compute energy, by 2040, we are supposed to hit the world's energy production capacity. So the increase in compute energy and compute demand has been increasing at a much faster rate than the world energy production capacity increase. So of course, this is not sustainable. One will either have to sacrifice from computing in order not to be unsustainable in terms of energy demand, or we have to come up with fundamentally new approaches, both from hardware and software fields, to improve the energy efficiency in computing. And again, the target is very ambitious, more than 1,000,000-fold improvement in energy efficiency. And this requires breakthroughs all the way from materials and structures to devices, circuits, architectures, to software algorithms and applications. So it needs reinvention of all elements from bottom up that go into defining computing and computing efficiency. And this naturally then needs contributions from multiple disciplines, including computer engineering, electrical engineering, as well as material science, physics, chemistry, and learnings from neuroscience that can guide the architectures towards being more bioplausible, for example. And we cannot cover all of this in this panel, but a few new approaches that we can remind here include in-memory computing with new unit building blocks as well as new interconnects, charge-based electronic or non-charged based devices where the readout can be not only electronic but also magnetic or photonic properties. To achieve this in a dense, high-speed, and low-energy manner is being the goal for all. And inspiration from neuroscience to guide the architectures that can go into these computing platforms inspired from how brain works, achieve brain-like connectivity with brain-like energy efficiency, which is the most energy efficient computing machine that we know. And scalable quantum computing is also a promising technology that in the future can give us the needed energy efficiency with computing. And all of this have to be supported with novel materials and process invention and development. So with that, I will go into introducing our panel, which includes world experts on some of these topics that will share their ideas and expertise with you. So I'm assuming my slides are out of the picture now, right? Okay, yeah, because I cannot see both at the same time. Great, so let me introduce our panelists next. As I said, we have a wonderful set of panelists who bring their expertise to discuss with us on novel paths for reducing energy consumption associated with computing. So first is Dr. Jesus del Alamo. Dr. del Alamo is the Donner Professor of Electrical Engineering in the Department of Electrical Engineering and Computer Science at MIT. He is a distinguished expert on nanoelectronic devices based on compound semiconductors and ultra-wide bandgap semiconductors, and also on novel ionic and ferroelectric devices for artificial intelligence accelerators. Our second panelist is Dr. Takashi Ando. Dr. Ando is a principal research staff member at the IBM T.J. Watson Research Center. He has made pioneering contributions from early research to productization phases of high-K metal gate technology, and this has enabled high-performance server chips from IBM since the 32-nanometer node and many of the early smartphone and tablet mobile chips. And third is Dr. Heike Riel. Dr. Riel is an IBM fellow and head of science and technology and lead of IBM Research Quantum in Europe and Africa. She is a distinguished expert in semiconductor electronic and optoelectronic devices, nanotechnology, and nanosciences, and she focuses her research on advancing the frontiers of information technology through the physical sciences. So welcome again, Dr. Del Alamo, Dr. Ando, and Dr. Riel. So I will start by asking questions and we can open and expand the discussion from there. So first, can you tell us about the technologies that you each are working on that has the potential to reduce the energy and CO2 footprint of computing in the following years to decades? So would any of you like to volunteer, or if not, I can pick one of you to start. I see Dr. Del Alamo nodding, so I will.
Thank you for inviting me to be part of this when I wanted to do this college here. Yes,
Dr. Del Alamo, I don't know if it's my speaker, but I think there is some noise in your voice connection.
Is it? I don't know what to do.
Yeah, I see a note from the producer that maybe your mic needs some troubleshooting.
Why don't you go somebody else?
Then I will go next to Dr. Riel as Dr. Del Alamo fixes the microphone connection.
Yeah, thank you very much for having me on the panel. It's a great pleasure being here. And the energy efficiency, which is part of this meeting, is really the key challenge in computing. And this is not something new, but I think the community has been working on the energy efficiency over many years. However, it's becoming more and more severe. And if we look at some of the I just want to give an example, also demonstrating that this is not something new. And I think this example, if you look at high performance computing and you compare today's high performance computer, for example, the IBM Summit system, which you may have heard of, which is a 200 petaflop system. It consumes 15 megawatt, which is quite a number at peak performance. If you go to the system before the IBM Sequoia, it had 220 petaflops, like a factor of 10 less performance, but it only had a factor of 2 less power consumption. So you see already within the technology development, there is a lot of improvements in order to improve the energy efficiency, and it's becoming more severe. With the future of computing, where we have different areas, and actually IBM works on all these different areas, and I let it to Takashi to talk about the AI part. But also in the conventional silicon part, in the entire stack, we need to improve. So if you look at this HPC system, it really starts from the transistor and it goes up into the entire stack, whether it's silicon photonics, which has been brought in, better architectures, etc., to not only increase the performance, but also reduce the energy which is consumed. And we are, as you mentioned, we are also not only working on AI accelerators, but we also work on the classical systems and also on the quantum computing. And in all of these things, we want to save energy. When we look at quantum computers, which I'm working on, then quantum computers, it's of course a completely new technology, which has the potential to solve problems which classical computers cannot solve. So that's one part, that you can solve problems which other classical computers cannot solve. And this means you get higher accuracy for certain problems, or you get also faster speed, or you can solve problems which can't be solved. Now let's look at the cases you want to test. No, it's still bad, actually. I think yes. So let me continue. If we look at the energy a quantum computer uses, and perhaps people mean, oh, this is a big system that we see in these pictures we know and have in our mind. Perhaps it consumes also a lot of energy, but that's actually not the case. Although we need to cool down the quantum processor to 10 to 15 millikelvin, which is very low, it does not actually take a lot of energy. And at the low temperature, the devices are actually in the superconducting regime where you have almost no dissipation. So if we look in the detail, and I think Dario also brought this, mentioned this in his presentation, then you have like 10 to the minus 16 watt per 2 qubit gate at 5 gigahertz for 100 nanosecond per gate. And so if you do the math and you look at the different energy consumption parts, I mentioned already the supercomputers, which needs megawatts, tens of megawatts. Then if you add up the energy a quantum computer needs, then it's a bit of the cryogenics, like 25 kilowatt. You have the room temperature control electronics, which you need, which is currently at 6 kilowatt. But also here, there is a possibility to improve. And then you have also like classical compute energy, which you need. So you come to about 35 kilowatt, which is really much lower than a supercomputer, and with a chance that you can solve problems which a classical supercomputer cannot solve, and also with having the chance to solve problems more accurate or much faster.
Thank you, Dr. Il. That was very helpful, both to hear that innovation at different levels of computing platforms are needed, but the numbers associated with quantum computing being 3 orders of magnitude lower, 3 to 4 orders of magnitude lower compared to the current supercomputers. That's very helpful to remember. Numbers stick. Right. Thank you so much, Dr. Il. So let's give the word to Dr. Ando next.
Hi, thank you for the introduction. Can you hear me?
Yes.
Okay. Yeah, as Dr. Yildiz introduced, my original background is the material development for the CMOS logic scaling. And that continues to be very important because no matter what new computing paradigm we introduce, the key is to tap into the existing data, which is growing exponentially. So we need a very dense memory and logic to be able to communicate with the data, large amount of data. So we think that the continued scaling of the baseline technology is important, and there's an still ongoing effort on that. But in the meantime, we need a new paradigm of computing. And my recent focus is to develop a new non-volatile memory, which can enable the deep learning acceleration with an in-memory compute. And what we believe is the existing non-volatile memory out there is developed for the memory application and not necessarily customized for the deep learning. So what we are doing is developing a new material and device from ground up that is more suitable for the deep learning acceleration, and build that into the state-of-the-art CMOS technology, such that we can prototype and show a proof of concept that it can be better than the incumbent technology. And for that purpose, we are having a consortium called AI Hardware Center, where we are working with the partners from across the many layers, like tool vendors and the device company and the metrology company. So we are making an ecosystem within the industry. And also we are collaborating with academia, like with MIT, I have been working with the faculty members for several years now. But in order to make an innovation from ground up, we think that it's very important to collaborate with universities. So we are making an ecosystem within the industry as well as with academia to drive this innovation.
Excellent. So thank you, Dr. Ando, hitting on this new non-volatile memory approach to low energy computing. So, and next is Dr. Della Lamo. Hopefully,
can you hear me now?
Yes.
Can you hear me now? Okay, good. We're back. Good. Thank you very much, Birge. Again, I'm delighted to be here. Yeah, there are three aspects of computing that my group has been working on regarding the pursuit of ultra low power electronics. And first, to perhaps come from the wall into the machine, there is all the power electronic side of things. Obviously, the computer is going to burn a lot of electricity, and the management of the electrical power coming in and being prepared with the right voltage under the right conditions in the different subsystems is extremely important to do it in a very efficient way. And for that, there has been great progress on wide bandgap semiconductors. And looking forward, there's a lot of interest in ultra wide bandgap semiconductors to do more efficient electrical power management. So gallium nitride today is an emerging technology that looks extremely promising, which is starting to find its application in many systems. Looking forward, there are ultra wide bandgap semiconductors that also look very promising that could potentially be even better than gallium nitride, such as gallium oxide, diamond, aluminum nitride, etc. So we have some activities in my group in that area. The second aspect of computing that is here to stay and is going to continue to require improvements in energy efficiency is the baseline CMOS. So even if we innovate new computing architectures and systems, CMOS is here to stay. It's going to continue to do a lot of the basic logic and is going to therefore continue to burn a lot of electrical power. And we need to continue to do our best to enhance the energy efficiency of what one could call conventional CMOS or roadmap CMOS. And in that regard, my group has been working for many years on various technologies. For quite a few years, we had a big effort around the world on indium gallium arsenide electronics as an alternative to do logic with at very low voltage. That didn't quite pan out for a variety of reasons, including manufacturing reasons. Today, there is still interest on tunnel FETs. These are tunnel BESS transistors, which offer the potential of working at very low voltage. And so I also have research activities in this area. And then the third aspect of all this is what Dr. Ando has just mentioned, which is new technologies for new computational paradigms to develop accelerators that are specialized on the specific computing applications that are going to be quite pervasive, quite energy consuming, and that we want to optimize. So we also have activities actually in collaboration with Dr. Yildiz also on new synaptic devices to essentially design, implement non-volatile analog resistors that can form the basis of analog neural networks for much efficient matrix multiplication. So I have two projects there, one with Birge on electrochemical devices and a second one on ferroelectric synapses. So this is a fantastic area of research, and we have many activities, and it's a lot of fun actually.
Excellent. Yeah. Thank you so much for this first round of answers where we touched advancing existing CMOS because, like Jesus mentioned, it will stay around, so we need to still work on its scaling, and quantum computing, as well as novel memory concepts, electronic or ionic, for analog energy efficient computing. So that's great. Then let's go to our next question. So we heard about the high-level description of these novel directions that you're pursuing, and I wonder if you could give us some specific examples of most exciting recent developments in these respective fields. So we can go in any order you would like, and maybe we can reverse this time and start Jesus first. Yeah.
All right, thanks. Thanks, Birgit. Yeah, it's the fields. These fields are moving very fast, and there's a lot of new results. I think I would mention, if I have to choose one, the recent research that we have been doing together, Birge, in the area of proton intercalation devices, which are these type of analog non-volatile resistors that can be programmed to take specific values of the resistance and can be held for a very long time. Birgit and I and other colleagues at MIT have been working on proton intercalation devices in which we're able to move protons, these are the ions in question, into a semiconductor, and then that changes the conductivity in a programmable way. And this is like a mini battery device so that you can put the protons in or take them out and the device will hold them in memory. And I think the exciting result that we have recently is that we have now been able to create a system that is entirely CMOS compatible, both in terms of the materials that are being used, in terms of the process technology that is used, and in terms of the temperatures. The temperature budget that needs to be used to be compatible with the backend, with the later part of the CMOS fabrication process. So this is tremendously exciting, and I am looking forward to making great progress in this area.
Thank you, Jesus. And I am so excited to hear that you picked this particular example among all the exciting work that you do. Of course, I can sound not objective, but very exciting to hear that. Great. So thank you again. And Dr. Ando?
Yeah, so as I mentioned, for the new computing paradigm, both scaling and the new elements are important. So on the scaling part, the important milestone is IBM proposed a new device architecture after FinFET to be a stacked nanosheet several years ago. And now it's adopted in the industry, and now it's becoming a new next generation structure. So that kind of continued scaling on the CMOS technology, that's one very important milestone to continue this effort. And on the new element part, I also collaborate very closely with Professor Yildiz. So I want to mention that, but it's already taken. So instead of picking one specific one, the overall in the compute in memory field, several years ago, the technology itself was only accessible by limited few people. So we didn't see much prototype or large-scale demonstration. But in the last couple of years, what we have seen is the foundry becomes available and the technology itself becomes widely available, including for the academia members. So we now see many prototype or actual demonstration at reasonably large scale. So that's the very exciting progress in the field of demonstration of the new computing paradigm.
Becoming more widely accessible and also motivating a wider spectrum of researchers, perhaps.
Yeah, it's growing. The field itself is growing because of the accessibility of the technology.
I am one example, right? I'm new for this particular research area, but it has been very exciting for us to learn and contribute to. Great. Thank you, Dr. Ando and Dr. Ril.
Yeah, so it's a very difficult question because you say we should pick only one. And I think in this field, there are really so many different things going on. And if I look at the, Takashi already mentioned the nanosheet transistors, which enable the 2 nanometer node, and also the energy efficiency, which is being achieved with going to that, is really super exciting for me, because I have started 2004 the nanowire project within IBM. And so we studied grow-silicon nanowires and 3.5 nanowires, and seeing that this gate-all-around architecture now made it to 300 millimeter and being really for the next node the solution is really exciting. And just to follow up on this, actually, when we started with nanowires, we worked on vertical nanowires because they were easier to grow at that time. And now seeing also that also on 300 millimeter vertical nanowires are built because they have the advantage of the gate length, right, of the short channel effects. Also here, the energy efficiency, which is critical because you have the off state at zero. The off state is much lower and things like that. So it's really exciting to see that these things come into fruition, but it also shows that there is a long lead time until it really works out, with a lot of hard work in between. I want to actually also mention another area which is more future looking in the classical world, or for the classical compute, which are making use of new materials of topological phenomena. because topological phenomena are something where I think the physicists can play a lot around, and they come up with great materials and great ideas how this can be used. And just recently seeing that, I mean, a big problem in classical is that the resistivity of copper is increasing with making the line width smaller, the dimensions smaller, which is actually getting a big problem because it creates heat. And so seeing that there are other materials making use of topological phenomena where the resistivity stays constant when you make the thing smaller, and they actually will win when we have to further downscale the line width, is really, I think, very exciting. And there is so much material research also still to be done in order to better understand, in order to find new materials, etc. The AI hardware, you have mentioned the project, so I don't need to go into this, but I think there are also many interesting new ideas which are coming up, but I think there is more needed, and they also, of course, all have to make the proof of reality, whether these are not just great ideas, good for a paper, but also for real implementation. And if I look in quantum, this is, of course, a very dynamic, very exciting field, quantum computing. It's developing now really fast, lots of progress over the last years, seeing it developing from 5 qubits in 2016, now having processors with 127 qubits, and following the roadmap which IBM Quantum has published, then this year we want to demonstrate 433, and then end of next year more than 1,000. So there's a lot of progress coming up. And of course, this all is rooted into new technology developed, further developing the technology, but not only the hardware, but also the software and the entire system has to be optimized. And important is here for us to increase the scale. This means the number of qubits, the quality of the qubits, which again entails a lot of materials know-how, device know-how and optimization, system optimization, and also the speed, that because in the end you're interested in how fast you also get your result of your calculation. So there's a lot of progress which has been made and is going on, and seeing this is really very, very exciting.
Thank you for sharing that, Dr. Il. So a few things that you have said, or maybe let's say if we summarize what we heard here, the advancements in the quality and number of qubits in quantum computing, and new ionic or electronic devices for non-volatile analog programmable memory for AI accelerators, as well as the initiation and now implementation of the 2 nanometer node, right? So these are all very exciting examples that you shared. And the years that you quoted, Dr. Il, brings me to my next question. So this particular example of nanowires that were initiated back in 2004, you mentioned, now are making their way into the implementation as the next generation node. And so that's about 18 years, right? So let's take that as an example, but going back to these exciting other, let's say, futuristic developments, what are the timelines that you think are associated with them? And again, a lot of hard work during that timeline that will have to go into them, from the current state to implementation in technology and applications.
So are you asking me or no?
In any order. So if you would like to take a first shot, Heike, that's perfectly good.
So I actually used a lot of different examples. So I think if I look at the topological materials and devices, right?
Topological materials for interconnect. It's a wonderful example. Right?
Yeah, I think that's something where, I hope that topological materials and devices will have impact in many different areas. And I think the example I've given in the resistivity may be one where, this could be in like a, I would say,
for example,
5 to 10 year time scale, right? But this is just a really rough guess, because we all know that we are as researchers typically too optimistic. So, yes. And then there are, of course, also using these phenomena for other applications, which still need a lot of basic research and technology development to make it then into some product. And I think when I look at quantum, there is continuous improvement, and these things are directly integrated. There is also analogies from the semiconductor things which we can bring in by optimizing in engineering. And it also needs, in the end, the full system. I think that's important that we always have the full system also in mind. Because in the end, it's not only about the qubit or not only about the AI hardware chip or the core, but it really needs the entire system to be more energy efficient than what we have and also show higher performance of what we have.
Great, thank you. And Dr. Ando, your thoughts about the timeline?
Yeah, so I mentioned about the analog memory elements for deep learning acceleration. And in that field, we are already seeing some use case for the deep learning inference, right? So it's already happening, but I think that the current stage is that it's similar to new non-volatile memory, finding appropriate space within the memory hierarchy. So I think the incumbent digital accelerator is so powerful, so I don't think the replacement will happen. So it's more like finding a right application space where analog AI shines, and finding such space is the current status, in my opinion. So I think for the deep learning inference using analog memory is for inference, that I think we are in that stage, and in the next 5 years it will continue. So once appropriate application space is fine, we will see more wide use case. But on the other hand, for the deep learning training, what we found so far is that the requirement on the analog memory is so drastically different from the conventional memory. So we think it takes a longer time, and we may need a more fundamental change in the device, not picking the existing memory, but we may need to develop a new memory. So in my opinion, that I expect that to happen longer time. So it may take 5 to 10 years is my outlook.
5 to 10 years. So we heard it twice now. Good.
Yeah, but for inference, I think we are already seeing something, right? Yeah.
For training with more data intensive aspect of the process, more time needed.
Yeah, some delay, but yeah.
Yes, but it
that's
will
my
get
outlook.
there. Yeah, great. And Jesus?
Yeah, well, we don't do products in university, so I can only talk as an observer of the time that it takes for new technology to reach the marketplace. And if you look in this line of business in the area of microelectronics and you look back in history, I think on average, it's taken 10 years from the point that a technology is demonstrated in the lab until that technology eventually reaches out the marketplace, is put in high volume manufacturing. I think Heike mentioned a few minutes ago just how far back she was already working on nanowires, silicon nanowires, and it's only now that they are in 300 millimeter and hopefully very soon in volume manufacturing. So and this is for technologies that we see them coming in our roadmap that is relatively well crafted. We are not talking here about technologies that don't quite yet have a roadmap for them to be introduced for reasons that Takashi just mentioned, right? In some cases, it's not clear how they're going to enter and how the competitors, the other competing technologies could be used. So we have to be ready to be here for a while to push these technologies forward, and hopefully eventually some of them will reach the marketplace and will make a difference.
Right. Yes. So maybe we can talk a bit more about this last point, that there are uncertainties for which applications will be the best targets for these new technologies, and there are technological challenges along the way that we have to work on. So could you elaborate more on that latter next, that this will take time, but what are the key challenges that the field has to work on, either specifically or from an approach perspective?
Should I start?
Why not?
Okay, all right. So I think, 2-3 years ago, as I saw emerging this whole area of analog neural networks and analog computing, I decided that I wanted to look into it and try to contribute. And what I found is that we have different levels at which one has to act for a technology to eventually reach the marketplace, right? Materials, devices, circuits, architectures, algorithms, etc. And what I found is that in this new line of computing, there are no clear interfaces in between the different abstraction levels, as we have come to understand and accept and appreciate in, say, CMOS conventional logic technologies. And the lack of these nicely defined interfaces between different abstraction levels means that a specialist such as myself at the device level can't just simply operate at the device level. We must be able to understand what happens at higher levels of abstraction and at lower levels of abstraction, which is why a couple of years ago we started working together, because it was also very clear that to really make a difference in this new area, we were going to need new electronics based on new material systems, working on operating with different physical principles. And so it was clear that we alone, sitting in our area of expertise, could not really make a difference. And that is why, well, luckily we started working together, where you guys brought the materials understanding and the fundamental concepts behind these proton intercalation devices. We brought in our expertise in device scaling, in device integration, device technology, and we're doing great fun stuff. So I think one of the challenges here to abstract this is really dealing with the lack of well-defined interfaces between the different abstraction levels for folks that are experts at different levels to find a way to work together. It is difficult. It is hard. We need to overcome that challenge.
Right. So it sounds like you're saying we have to re-establish interfaces between the different levels of work that has to go into completing the whole system as a new and energy efficient platform. Okay, so because like you said, the current technology is well defined and those interfaces have been established over a long time period and they are working well.
Yep.
So someone working on semiconducting materials topic knows which device person to talk to, the device person knows which circuit person to talk to, and so on. But now everything being reinvented needs to reestablish those interfaces, I think.
Right, and we have a language at the interfaces that's well established.
That has to be redeveloped also. Right. Yeah, that's very good. Yeah, so other perspectives from Dr. Riel or Dr. Ando?
Yeah, so for me, the biggest challenge is that at the high level, for the deep learning area, what we are trying to replace is not the saturated or mature area. The digital accelerator is still a very hot area, which is growing exponentially every year, right? So the replacement of that is really difficult because it's a moving target and it's still a growing area. So in order to show usefulness over the digital requires demonstration at scale. So this is a new paradigm and new technology, but proof of concept is not enough, but we also need to show the scalability at the same time, because we are trying to replace the exponentially growing new field rather than replacing the mature technology, right? So showing the proof of concept and scalability at the same time is proven to be very challenging, and that's where we put more resource to really enable.
Yeah, that's a very good point also. So maybe in the field we produce perhaps more proof of concepts and than those that are actually scalable. So to identify those that can be scaled up and to demonstrate them is what you're saying.
Yeah, and in order to do that, I think we need to expand the ecosystem and work with players in different layers of the stack, like not only device but also the software and applications.
Right.
So I think larger, more concerted effort across the entire layers will be needed to really enable that. But that the scalability and the proof of concept at the same time is the biggest challenge to me.
Right. I guess this is the case in every technology, right? So here we are talking about energy efficient computing technology, but in energy conversion and energy storage area too, the challenge is not only to demonstrate proof of concept in the lab, but to be able to demonstrate that it is scalable, it has enough production rate, it has enough capacity to be technologically viable.
Yeah. I think in the CMOS scaling era, the roadmap was clearly defined, right? In that case, we can do proof of concept, and then industry can take the nugget and
the target
put that on the roadmap.
The target
but
is
now we are defining stage of the roadmap itself. Therefore, the nature of the collaboration between academia and university needs to be longer term. And
Yes.
I think that is the biggest challenge that I see for this new field. But that's also an area very exciting for the new innovation.
Right. Great.
I think following up on Takashi, I think it has changed when you go back like 10, 15 years where there was a silicon semiconductor roadmap. It was clear what to demonstrate over the next couple of years and what's need to be done. So all the different advancements which had to come together, whether it's lithography, whether it's material, whether it's the transistor, whether it's the back end of line, it all was kind of clear what needs to come together at which point. And it was like one general processor. But right now, with getting more energy efficiency and more performance out, having all these different options, it's also more difficult to develop all this in the holistic manner that you can really also use it in the end. Right, that you can integrate it in the system. And so finding the right path of making it still feasible to develop this diversity of different things for different applications, and still making it in a way that it allows companies also to create some return of investment, because that is, I think, this is itself is a challenge, I would say, right? And then if I look at quantum computing as the big thing here, the big challenge, and also the big thing and milestone we want to demonstrate is quantum advantage. To say, okay, this is one example where quantum computers can solve a problem which cannot be solved by a classical computer, or provides value to companies. And of course, to reach this, we have to improve what I mentioned before. We have to work on the scale, on the quality, on the speed, and then you can dive into these things individually, and you find little different challenges which have to be solved on all the different levels, from the material to the systems architecture.
Right. So thank you for that. And I think a common point that I'm hearing from all of you is that everything at different levels are being reinvented, and we have to reestablish connections, develop these in parallel, and not only show them individually at proof of concept level, but scale them, connect them, so that they become a viable technology. And that's a big challenge, right? And you also mentioned that like different disciplines, different people have to come together to work on these. And maybe that's a good transition also for me to ask, what do you think about leveraging interactions between academia and industry more closely? So we're at MIT, we're already very lucky to be able to collaborate with industry, including IBM, new colleagues, and it has been really exciting for us to understand the challenges and work with you to advance these technologies. So what are your views about maintaining that, flourishing that, advancing that for overcoming these big challenges in the field? I guess through this interaction, we're also both learning how each party works. Right? So industry has a technology target, and academia maybe comes from, again, more proof of principle level. We understand what the industry's goals are and challenges are, and maybe industry learns how the academia works and tries to leverage that. And what are your views about getting the best out of that interaction? Maybe
I can start and give my thought. I think what you mentioned is really very important, that the collaboration is providing many different synergies for everyone, and many win-win positions, because on one hand, it's important collaborating from the university side to also fully understand what are the challenges, right? That you also go after the right things and also useful and have an impact. But on the other hand, it's also from the university, I think, very important to create the basic and fundamental understanding of the things, because only if they have the basic and fundamental understanding, then you can really fundamentally improve things or create new things. So I think that's a really very important part. And that's something which is more and more difficult to also do at a company. So the collaboration here can be really very fruitful. And so I think there is also not the shape or form of a collaboration. It can come in really many different flavors. And in the current world where we really have to be very dynamic, very agile, very fast, and there are so many different opportunities, of course, then collaborating provides to everyone also the speed and the agility and more impact.
Thank you. That's wonderful. And Dr. Ando?
Yeah, so I have been working with academia for the last 15 years from the industry side, and I think the nature of the relationship has been changing. Yeah, as I said, when we had a roadmap and we are working on some technical topic, the collaboration can be short-term, like 1 year or 2 years, and when the student graduate, we can stop. But as far as we have good publication, that was a good collaboration, and industry side can take the key parts from there and go on. But as I said, we are defining stage of the roadmap, and in order to show usefulness over incumbent, we need to prototype instead of just publishing, right? So that requires longer term collaboration. So I think what we are looking for is a longer term relationship, and also from publication oriented to actual demonstration or prototype oriented in my area of research. So that is kind of a change I have been seeing.
Right. And that's also consistent with what you all said, right? This is so new. The targets are being defined along the way, and that renders the challenge to be longer term and the interactions to be longer term too. So yeah, that's helpful. And maybe we can hear from Dr. Della Lamo the academic perspective.
Looking from the academic side, I think a motto of MIT could be the dignity of useful knowledge. We really have a lot of respect at MIT for knowledge that is new, is true, a true contribution to the knowledge of the world, but it also is useful. And we can work, particularly in this new area where we are talking about new material systems, new physics of operation, new device physics, etc. We can work on many different kinds of problems, many different material systems. We need the guidance from industry to tell us what lines are likely to be most promising to impact the world. We have a vocation to impact the world. And so that guidance that comes from industry is truly essential for us to be relevant, which is something that we really, really want. So I'm delighted with the very close collaborations and long-term collaborations that we have with IBM, because they're really helping us to pick up problems and directions that are particularly promising.
Great. So what I'm hearing is that the guidance on the important problems from industry is absolutely important for academics to focus on the right problem, and it's helpful to industry to leverage the novel and perhaps deeper science and engineering that could arise from academic work, and redefine these targets and boundaries together. Great. So that was very interesting discussion. And the next question I want to ask is, how do you think we can leverage what the field learns from how the brain computes, right? So the most energy efficient machine is the brain. So it's pretty much an electrochemical machine of taking data, making sense of it, and taking actions based on it. And there are a lot of very exciting advancements going on in neuroscience, experimental and theoretical neuroscience, in trying to understand how the learning and processing works in the brain. And what do you think we should do from hardware for computing side to interact with and learn from and translate to hardware from neuroscience?
I think it's actually the best question. It's really very, very hard to answer. Because we know the brain is super efficient for some tasks, not for all of them, right? Because for some tasks it's completely not useful.
Yes. It's true. Yeah.
And
So
so, but
whatever it can do, it does it very efficiently.
yes, but for some of the tasks, exactly, it's very, very efficient. That's for whether it's image recognition and all these type of things, right? And so it only needs 20 watt. So unfortunately, we have not yet fully understand how the brain really works. And there is research going on for many, many years. And there's a lot of things going on for trying to image it, trying to model it, many different ways of how to understand it. But we are not yet that what is known can be really applied to something which we build. So, I mean, if you look at the accelerators Takashi mentioned, right, and also what Jesus and you mentioned, then it's still kind of trying to solve mathematical functions in a better way, which are part of deep learning, machine learning, etc. Right? I mean, in the end, what we do right now is like matrix multiplication, trying to make it better, faster, more efficient, parallel, etc. So this is not yet. I mean, bluntly, that is not yet mimicking the brain.
Mm-hmm.
And mimicking the brain, what people have done with the spiking neural networks, that's it's kind of it's a start. Let's put it this way. But there is still like learning algorithms and all this is missing. So we are really at the very, very beginning of really mimicking or building something which works like the brain.
Mm-hmm.
It's exciting and exciting research. And this is actually also part where I think the universities can be really strong, because I think for the companies, it's a bit, okay, I can't use it in the next 20, 30 years, probably, most likely. But it's a very fundamental problem which should be solved. And also with the techniques, like the imaging, which is getting better. What we learn from looking at the brain under different functions, from the modeling capabilities which we have, and all this, bringing this together, it's a really huge task. But I hope that step by step, we come to a solution.
Mm-hmm. So maybe what you're saying is that this is yet another interface that we need to establish and build upon. So maybe the traditional computing architecture never cared about interfacing with neuroscience. It's materials to devices to circuits, architectures, algorithms. But the interface with neuroscience was not needed perhaps until the growing interest in intelligent machines, but also to do that in a very energy efficient way. So what can we learn from the brain
and also like directly interfacing with the brain, right, is still also,
yes,
I would say, in a very rudimentary way what we do.
Yes. Yeah. And maybe some of these devices that we are working on for analog non-volatile processors, we can use them to emulate, let's say, the biological process, but maybe in the very long term, they could also interface with the brain to assist the neurological side of the process. Right. Yeah. And Jesus?
Yeah, I don't have much to add beyond what Heike has said. I know nothing about neuroscience. As you know, we are trying we're working with colleagues in neuroscience at MIT. This is a good topic for a university like MIT, where we have world-class expertise in many different domains, and we can come together and try to do something together. And we are finding, talking about the interfaces again, that we don't talk the common language. We don't talk a common language. It's difficult to communicate across the boundary. I have to say, though, that on the educational front, we are doing things, and I think this is relevant. So maybe 2-3 years ago, MIT introduced a new major, which is at the interface between electrical engineering and computer science and neuroscience. I think is labeled 6, 9. 6 is electrical engineering and computer science, 9 is neuroscience. And the first graduates are coming out this year, if I know this correctly. So this is what we need, right? That we realize that at that interface, there's a lot of good work to be done, and we need to prepare students that are specialized on the interface, that can understand both languages and serve as a glue for these two big fields to come together and work together.
Yeah, I agree. So training the next generation at that interface would be very helpful.
Yeah.
Those who are already in the field and have been traditionally trained in the separate disciplines maybe find it hard to communicate, but maybe the next generation, it will become natural to them if they are already trained at the interface.
Yeah.
Right, that's very exciting. And Takashi, would you like to add?
Yeah, I think I echo with Heike, and I don't have much to add, but yeah, I agree that we are mimicking a few features of brain, but not necessarily implementing the mechanism or secret of learning itself, right?
Right.
So it's very difficult to go beyond just the energy efficient deep learning at that stage. That's very important, and we should push that. But in parallel, we need to learn more from the learning, the mechanism or secret of learning itself. That needs to be a parallel effort that we need to always continue.
Right. What are the learning rules, and can we translate them to hardware implementation? Right. Something we should push for together. Thank you. Yeah, I think we covered all the questions that I wanted to specifically ask you, and I can leave it open to you now if you would like to add any additional points or ideas or questions that you would like to pose, and any last words that you would like to share.
Well, since you give us a chance, Bilge, I'd like to put a plug for a new program that we are launching at MIT, which is the MIT AI Hardware Program. We are about to make it public, perhaps any day now, which is a new consortium of companies that are interested in AI hardware, that are interested in connecting to a community at MIT of folks at the different levels, as we have been discussing in this panel, that are relevant for AI hardware to bring us together and to start working on these interfaces and start working together to try to innovate future hardware to make AI vastly more efficient and capable. So it's about to launch. We are excited to start working together with a number of companies, but we are open for more companies if they want to join us.
Very exciting. Thank you for sharing, Jesus. Excellent. Great. And Takashi, Heike, if you would like to.
Yeah, so I believe many students are also listening this, right? And yeah, when I speak with students, and in their mind, AI is all about coding and application, right? But I want to emphasize that true innovation comes from device or material or hardware, right? And it's an exciting field. So I want to share that with a student working on hardware. And
excellent.
I want them to feel encouraged. And I think burden is on us to actually show it's cool. But I think at least I can guarantee that it's an exciting field where they can grow. So I hope many more students working on hardware joining this journey.
Right. Physics and hardware wave AI is super exciting, and we need fresh and engaging and curious minds to join this. Exactly.
So I want to add, actually, because I think that the innovation or the biggest innovations will come from people working across the entire stack together. And we gave the example of understanding the brain, where you also need all the different people kind of working together to really then bring transition something into hardware. And I think also of everything which we right now do is building more system optimized solutions, which are more energy efficient and more performing for this specific task. And the innovation is really now more at the interface, where the different, people, the different problems come together. We have over many years worked everyone in its own island, right? The device people, the circuit designers, the software people. And I think now we can't escape. And that's now we have to really learn a bit the language of the others and do step-by-step work to closer together to optimize the system. And that's also, Takashi, for the students important, right? You already touched the students, that you try to open your view a bit and you learn also about the other side, what they're doing, and be able to talk to each other and form really multidisciplinary groups in order to tackle the big problem which we have, because it's a big problem. We have to get more energy efficient.
Great. So I will conclude by saying that interface is the key word to remember from this discussion. Interface between the different levels of components that go into the system, but also interface between different disciplines, going from physics to engineering to neuroscience, that all have to come together and contribute to making this happen. So thank you so much to our panelists, and I will turn Now to a few specific questions we have been receiving from the audience, and I will read them out. And again, you can go in turns or volunteer how you would like to answer. So the first question is from the audience. We are approaching in the next 20 years or so the Shannon von Neumann Landauer thermal limit. How can we address this limit? Big question.
So I have to admit, I don't have a very good answer. There are certain compute, areas where you talk about adiabatic computing, etc., but that has not really yet paid off. And I think there is, it's a very important question, what is beyond, but I think there is a lot of research which needs to be done specifically on this, and this is not yet done.
Mm-hmm.
I have to confess ignorance, but since the word thermal is in it, I think the strong interest in the last few years on quantum computing, which takes place at extremely low temperatures, has somehow revived the interest on low temperature electronics.
Mm-hmm.
And the performance of CMOS and electronics in general improves very fast as you come down to low temperatures. And so perhaps that is a path for addressing this limit.
Good. So I can go to, thank you for that, and I can go to the next question, which is, what are potential examples of CMOS compatible quantum computing designs, and where might we see these first being applied? Heike, I guess this is for you.
I guess that's for me, but I have to admit, I'm not really sure what is meant by CMOS compatible quantum computing designs, I have to admit. So I think what I want to add to this, I mean, we have quantum computing, which is based on the laws of quantum physics, and that's a very different way of computing. We can't go into detail. And then there's classical computing. What is definitely for the future is that these two computers, they have to work very, very well together. Because you have still a classical input side, you have the quantum computation, you have the classical output side, and you also have algorithms where you need an interplay between classical compute and quantum computing. And so the architecture and how classical and quantum works together, also with memory, is critical, and there's also a lot of innovation going into.
Thank you, Heike. Okay, so I see one more question. What are the key partnerships across industries that you envision being most critical to increasing adoption of more efficient computing architectures? Key partnerships across industries. I think that's the question, the key part of the question.
Okay, so let me take this. So yeah, as I said, in order to show improvement over incumbent, it needs to be a large system. And no matter what the new architecture is, that needs to interface with a large amount of logic computing and the data. So we need a dense memory and logic. So, and no single company possesses all the technology for that. So I think the partnership between logic, memory, and the new element, that needs to happen. So we don't think any single company can cover all of them. So the ecosystem is needed, and multiple companies having different expertise area needs to work together to enable such new architecture.
Mm-hmm. Thank you, Takashi. Would Heike or Jesus like to add?
I mean, what we see in the quantum computing area, for example, is that there is also to be the full ecosystem to be established, right? You need a cryostat, you need room temperature electronics, you need certain lines, etc., and all this. Also, the supply chain of this new compute area has to be created. That one company doesn't need to do everything in the entire system, but you can also have valuable suppliers which provide certain areas where the company you may not want to focus on.
Perhaps what I would like to add, the question is about partnerships across industries, but I think the partnerships have to go beyond and really include academia. I think there is a lot of innovation that is really needed here. We are talking about altogether new device classes based on new materials, new device physics, and that's what universities bring to the picture, that fundamental innovation that eventually, through the ecosystems that Heike and Takashi have mentioned, hopefully will reach the marketplace. So I want you to count universities as part of those partnerships.
Absolutely.
No,
Yes.
and I think that's a really very important point, because the very new ideas, leading ideas which you can test, there are the universities are really key. So I think we answered it now. Takashi and myself answered only the question which was asked, but I think really it's important to have a collaboration across all the different things, because it has everyone has its role in this in order to really have a fruitful and positive, successful outcome. And I think there are also very nice examples, like the SRC JUMP program, right, where you have different industries coming together, defining what the research is they need, and then providing also funding into a pool where universities can apply for these certain calls. So this is one mode of collaboration. I mean, we mentioned before there are different modes of collaboration. There are direct individual collaborations, but there are also for kind of how are they checking out what ideas are on the market, and then supporting these ideas and the early development. These type of private-public partnerships are also very important.
Right. The following question is somewhat related to that. How can we incentivize these partnerships across industries, but also between academia and industry? Like the SRC model you gave is one example, Heike, where the industry provides a pool of funds for academic partners to join the problem and work together. And that's a very helpful model. Are there others that you can recommend for the field to consider?
Well, let me comment on that model, which is a helpful model, but it can be improved. Right. And it can be improved in two directions. One is the treatment of intellectual property, which is these days it's becoming such a stumbling block to be able to work together, particularly across the academic industry line. And I think we just have to, particularly as we talk about very fundamental problems that are going to take a long time to eventually render industrial practical deployed solutions, we should just be willing to work in a open environment where we just put all our new findings open to the world at large. And then that eliminates one of the big stumbling blocks here, which is to find an IP agreement. It's such a big problem in these collaborations. The second one, and I hope this doesn't sound like whining, is this is very expensive research. We run very expensive facilities. We have very complicated equipment. It needs to be maintained by very specialized personnel. Our materials are expensive. What can I say? The research funds need to keep up with the real costs of the research if you want this to make a difference. So I would encourage, as companies look at working with us, to really sit down and listen to us as we put a budget together to understand why things are so expensive. But this is the reality of the situation. We cannot work around it.
Great, that's very helpful, Jesus. And Takashi, would you like to add?
Yeah. So to give a different angle, I think if we have one killer product or application out there as a result of the collaboration, it's naturally incentivized. So I think having some useful product or applications out there as a result of the collaboration is important first step, and then the rest of the step naturally follows. We need to think about incentive, etc. if it's very successful case. So we are in the stage of really trying to enable that, and that's very important to get this going.
To demonstrate some success stories that come out of the collaboration, to incentivize both sides more. That's what you're saying. Yes, very helpful. And perhaps also to get more support from the government to enable collaborations between industry and academia without IP restrictions, right? So Jesus mentioned about the IP-related challenges in working with SRC, but if some support or increased level of support come from federal sources that give more freedom for the academic research and the IP that may come out of it, but still enable collaborations with industry. That may be another model to call upon. Great. One last question I see is following up on a point that Takashi mentioned, that is the importance of having students trained and involved in AI, hardware, physics, materials, innovations, not only from software, right? And the question is, what changes or new educational programs should we start to enable this interdisciplinary thinking? Typically, we have traditional departments that educate in computer science or electrical engineering or physics, right? And one example that Jesus gave was a new joint program between neuroscience and electrical engineering. So maybe we should create and foster more of such interface natured disciplines between traditional disciplines. So if you can think of some examples to share.
Yeah, let me jump in. I actually feel very strongly about this.
Yeah.
You know, we have what one could call an existential challenge in the hardware disciplines, as they relate to microelectronics, which is the fact that undergraduate students are not choosing these disciplines to study their majors. Students with interest in science and technology are mostly going towards AI, computer science. And this is a big problem because we're really starving the pipeline that would eventually lead to graduate school and to jobs and innovation in this area. So I think the biggest educational change that needs to be made, we really need to come up with meaningful, exciting educational experiences at the freshman level and at the sophomore level to attract the students with interest in science and technology to have a good look at hardware-based disciplines and to realize that they are immensely satisfying, that there are fantastic careers, and there are careers in which they can really shine. And I can give you as an example that this last fall, I ran a freshman seminar. So these are first-term freshmen coming to MIT. I ran a freshman seminar in which we brought the students into the clean room of the facilities of MIT Nano once a week for 3 hours over the entire term to fabricate silicon solar cells, to go through the process, to think through the process, to characterize them, to understand the models, and then to do it one more time, improving the process and improving the efficiency of the solar cell. The students were really delighted. So we not only got these 8 students, this necessarily has to be a relatively small group, really enthused about semiconductors and nanofabrication, but we also qualify them to be able to do research in the clean room facilities of MIT. So they can, if you want, sell their services to advisors now and bid for research programs as undergraduates to support research in hardware, in nanofabrication from their second term freshman year. I think it's experiences of this kind that we really need to introduce to attract more students to microelectronics disciplines.
That's a wonderful example, right? So giving them the first-hand experience that this field is exciting once you start working on it is a very good one. And so at the institution level, we can initiate more such cross-disciplinary programs. And maybe another point is in line with the spirit of this workshop, right? Computing has a tremendous impact on energy and sustainability. And this has to be taught to the students too, that there is a motivation to save the world, right? And computing is a big contributor in that direction. We have to come up with solutions to make computing more sustainable. And doing that only from software and algorithm side is just not going to work alone. So if we can convey that message to the incoming students, I think that can also help, because many students come with the goal to save the world, right? They want to do something impactful to save the world, and this is one of the important challenges that we have to overcome. So I guess it has to be told out there to the students as well.
I think, Birgit, that's a really very important message, because I think in the electronics and electrical engineering, physics, we are often not so good sellers of the importance and of the impact of the work which is done in these disciplines. And here we have to, I think, adapt probably our communication ways or storytelling skills a bit better, and really make the purpose which is there, right? Because without the semiconductor industry, without these things, we wouldn't have the video call, we wouldn't have a watch, we would not do anything almost now. And I think showing this and educating people about this, what the purpose is, and what the impact is, that can also inspire more students to go into this field.
Yes, yeah, impact not only in terms of enabling like advanced technologies that support our modern life, but also impact in terms of making computing more sustainable for the entire world. I think that message we need to communicate to them. And so this workshop is a wonderful opportunity for that. Hopefully we will have more of them. And that is time to end this very exciting discussion. So thank you so much, Dr. Ando, Dr. Riel, and Dr. Delalamo for joining us for this workshop and for this panel and sharing your ideas for our field. Thank you so much. And I will say that then this brings our second day of this workshop to a close, and we greatly appreciate everyone who has been involved in this workshop as a speaker, moderator, and participant. And the learnings from these past 2 days will be disseminated to workshop registrants along with some recorded elements. And so also please stay tuned to our next workshops in this space. So thank you so much for your participation.
Thanks. Yeah, bye-bye.
Thank you very much.
It was a pleasure. Thank you very much, everyone.